from online and on-site. So this is session 11 and about 6G wireless communication networks. At first, we have 3 invited speeches. Yeah, the first one is from Associate Professor Islam from Independent University. His talk is about prospects and challenges on an EOG-based human-machine interface for physically challenged people. Professor Islam, are you here?
Hi, Professor. Can you hear me?
Yeah. So you can start. Yeah.
Sure. Thank you very much for the invited speech on the prospects and challenges of an electrohologram-based human-machine interface (HMI) for physically challenged people. So I'm an associate professor and a lab head of biomedical instrumentation signal processing lab from Independent University of Bangladesh. So this is a brief outline of the presentation. So before that, I would just like to introduce our lab, our medical instrumentation signal processing lab. So it's a very small research group where we do research on the use of electronic signal processing and machine learning for the applications in biomedical and similar areas. So this is a brief outline. We'll talk about the motivation. We'll talk about the electroencephalography and EOG, electroholography, and then we'll talk about why EOG-based HMI has been proposed. And then we'll talk about the system that we have proposed so far and the testing of the system. And we'll also show some example application like wheelchair control, computer mouse control, and prosthetic arm control. Then we'll finally conclude with the limitation and future work. So motivation starts with that there are, according to statistics every year, around 250 to 500,000 people suffering from spinal cord injury. So what happens when people suffer from spinal cord injury? They have almost get paralyzed from neck to all the way to down to toes. So they cannot use their fingers or arms to do any typical daily activities. So that's the motivation, first motivation. And then from our country's perspective or similar country, we found that there are a lot of road accident and a lot of building collapses, so which actually results in people losing their control of their hands or legs, they're losing their arms. So more than 4,000 people get injured in road accident every year in our country, and some of the examples like Rana Plaza massacre back in a few years back, where there are thousands of people that lose their life and they got injured. So from that point of view, we thought that we would like to propose some kind of system where it can be affordable, easy to use, and finally it is designed for the developing countries. So we'll start with brain-computer interface system. So typically the non-invasive brain-computer interface system are very popular because the signal modality is non-invasive. And among the non-invasive brain-computer interface, EEG, electroencephalogram-based ECI is most popular because EEG is easy to, it's low cost, easy to use, compared to other brain recording techniques. But the problem with this kind of brain recording technique is that brain signal is very complex, and it is basically required very high complexity signal acquisition device, signal processing and classification models to actually decode the signal based on the intention of the user, what the user wants to do. So it is typical brain-computer interface system where the signals are recorded from the brain. The signal acquisition devices like EEG, they are quite costly, and these EEG devices, the commercial available EEG devices, they require license to actually use the raw data. So mostly their clinical use are good, but as far as brain-computer interface purpose, you need the raw data to actually decode the signal and to be able to use it for the control of the device. So in that case, this is something that you really need to build your acquisition device by yourself. And EEG signal is not very easy to record with your development. So then we do the typical pre-processing of the signal. We extract features, do the classification based on the user's intention. So it can be in a computer control. It can be a control of an electric wheelchair or control of prosthetic arm. So that means that the target people who are physically challenged, who are suffering from spinal cord injury, or due to accident or disease, they have lost the control of their typical arm. So that's our legs. So that's the motivation. Now, as mentioned, that EEG is very complicated medical signal. It's non-stationary, non-linear, and it is very noisy. On the other hand, in EEG, there is EOG. So EOG stands for electroculography or electroculogram, which actually measures the cornea retinal standing potential between the front and back of the human eye. So whenever we do the eye movement or blink our eyes, there is some kind of deflection in the signal, which can be used to record EOG or electroculography. So we have horizontal eye movement and vertical eye movement. Now, when people record EEG like this, EOG comes as an artifact or noise. Some non-neural sources. But EOG compared to EEG is easy to detect, and it is less complex in terms of signal processing or acquisition or classification. So that's why we wanted to use EOG instead of EEG, because the acquisition device design or development of the EOG device is easier. The computational complexity is much easier compared to EEG signal processing. So moving on. So these are the reasons that we prefer to use EOG, not EEG. So we are actually moving from brain-computer interface, controlling external device through brain, instead of we're going to control the external devices through our eye movements and eye blinks. So that's the proposed system. So instead of recording EEG or brain signal, now we'd like to record the eye movement and eye blink. And then we'd like to use this signal, decode the signal, and we have developed this EOG device, and then we'd like to control these three appliances, or devices externally wirelessly. So one is the electric wheelchair, another is controlling of the computer cursor, another is controlling of the prosthetic arm. So this is the development of the EOG acquisition system in our lab that we have done. So first of all, we developed a two-channel output. That is the output, two-channel output EOG acquisition circuit. This looks like this, and this is the student that has developed and has tested. And we can see that we can detect the left eye movement, right eye movement, as well as blink. Similarly, we can detect horizontal eye movement and vertical eye movement. And then we move to modify the circuit and develop this system into a four-channel output, four-channel multi-pulse signal acquisition. So this circuit or system, that it will provide, not only it can record EOG, but also it can record ECG, EMG, and sometimes EEG. But EEG will be single channel device anyway. So the idea is that we have made this possible by allowing the gain and frequency to be controlled through some tuning of the scope, so that whenever we need that, we can actually switch from EOG to EMG or EMG to ECG, and so on and so forth. So these are the technical specification that we have done. We'll not go into much technical details, so let us see. So we have tried to validate that as well. So we wanted to classify the eye down movement, left movement, right movement, up movement, blink, eye blink, and all this stuff. So although it has been tested for only one subject, we found that validation accuracy is nearly 100%, but obviously it is required to test on more subjects. So what we have done, we have used the weblet transformed as a scalogram as an image for the training of our machine learning model with these different classes of EOG. So what are the potential applications? As mentioned, that it is a multi-purpose wire signal, although initially it has been designed to record EOG electroculogram, but later it has been, it can also record ECG, EOG, EMG as well. So, which means that we'll be able to control the mouse cursor through these EOG signals. We'll be able to control the electric wheelchair through the same EOG. We'll be able to control the robotic arm or prosthetic arm either with EOG or EMG, because EMG can also be used, can be recorded with this newly developed device. And this device can also be used as a portable, ECG machine or any other biomedical signal recording machine and analysis machine. So it can also be used as a bioremote controller to basically controlling electrical appliances through your eye movement and eye play with a maximum range of 100 meters. So that actually tells that the physical challenged people who cannot use traditional devices or press the button or press the switch or cannot use the smartphone, they will be able to basically control, and they can be their quality of life can be somehow be improved. So this is an example where we can see that with the help of our eye movement, we can control electric wheelchair. So this is the wheelchair that one of my colleagues in my university has developed. This is a makeshift wheelchair. You can see that it was a traditional chair, and then it has been converted to an electric wheelchair. So previously, it was motivation is that people can use this button switch to control the right, left, up and down movement, front and back, backward movement. But later we thought that what if the person, this patient or the user who is using this wheelchair cannot move their finger or doesn't have an arm because of the accident or injury. So in that case, we said that how about moving the chair with the help of eye movement and eye blinking. So that's the motivation. So let us play the video. That they are not very visible to his eye. Yes. And yeah, so this is one example. So moving on to the next, this is another example where we can actually use our eyeball movement to control the computer cursor. So we have 4 different eyeball movement, 2 horizontal and 2 vertical plus eye blink. So 5 command can be generated easily. So with this help of this 5 command, we can actually use, we control the computer cursor, and we can use the on-screen keyboard to type something if we can use because we can use the computer cursor. So initially the video may look like very simple verse, so unique about controlling the cursor, but the controlling of the cursor has been done by eyeball movement. That is something that very unique. So let us play this one. So you can see that the signals have been received in the hyper terminal and is actually using this EOG eyeball to control this. So obviously the degree of freedom is not very good because you have only 4 different directions, and you can use your eye blink twice to actually click on something to open something. So which he has done, he has actually opened a browser, Google Chrome browser. So this is an example demonstration. Well, we have also tested the classification performance on 5 subjects, and we found that the average classification accuracy is more than 85%, which can be obviously improved with tuning of the classification and feature extraction parameters. So this guy actually opening an YouTube video with the help of his eyeball movement. Yeah. So moving to the next one. This is an example of controlling your prosthetic arm, 3D printed prosthetic arm inbuilt, printed in our lab. But this time we are using EMG signal. So that is the electromyography, the muscle signal, electrical activities of the muscles. But although we are saying that we have used here EMG-based signal to control the prosthetic arm, we can also use EOG, as mentioned before, to replace EMG, and you can use EOG to do the same thing, to do the same controlling of the So this is another example. So let us see the video. So everything is recorded and real time so there are it says that you can move your fingers to grab something. Also, pick up a small object. So this is a real time signal that we also monitor horizon. So, yeah, in conclusion, we can say that EOG electropholography based HMI has a good potential to be used in future non-invasive human-machine interface application. And the reason is that EOG signals are much more less complicated. It is easier to design the acquisition devices. It requires lower computational complexity for processing classification. So that means you can build a more user-friendly and more portable devices with the help of EOG compared to the existing EEG-based systems. Challenges are, so far we have actually tested individual applications like controlling wheelchair, controlling mouse cursor, controlling robotic arm or prosthetic arm, whatever you say. But integrating all of them in a single system as a single system obviously has technical challenge which we would like to cover and make it up in the future. Too much intentional eye movement because you need an intentional eye blink and eye movement to actually do this because we always do eye blinks, right? These are unintentional. So we have found that intentional eye movement can be separated or detected from unintentional eye movement. So we only do intentional eye movement when we actually want to control the devices through EOG. So this kind of intentional eye movement requires a bit of pressure on your eyes, so it can be stressful sometimes for the subject. So that's the challenge. The system is highly user specific and highly customized because if it is trained for one single user, then it might not be trained for another user. A new user must also change their eye movement and eye blink again. So, and lower degree of freedom at the point of time it has lower degree of freedom. You can see that the number of movements is very limited. For example, it has 4 movement. It cannot go diagonally, right? It cannot have much more. So low degree of freedom is an issue. But again, if you think about non-invasive EEG-based BCI, the degree of freedom is similar. But whenever you think about invasive signal, EEG-based BCI, then invasive one, they have higher degree of freedom because the signal quality is much better than the non-invasive one. So in future, as mentioned, I would like to integrate all the 3 subsystems to make one single. Would like to experiment with different type of subjects, and finally would like to apply for a clinical trial, and hopefully we can do the trial and do the performance validation at that time. So with that, these are the few selected references that have been published. So I'd like to acknowledge my group and its members, my Department of Electrical and Electronic Engineering from Indian University, Bangladesh, and IUB sponsored research and conference grant, my students, collaborators, and co-authors to help me with this research. So I'd like to thank you. Thank you very much.
Yeah, okay. Thank you, Professor Islam. Do anyone has some problems? Have some questions to ask?
Yes, please go.
I have one simple question. I wonder if you if this software or and hardware the system can be commercialized. Is it possible to be commercialized?
Motivation is to do the commercialization, but before that, you have to do a lot of testing, do the clinical trials and everything. Only then we can go for this approval. But at the moment, it is still this different subsystem and prototype based, so it requires a long way to do the commercialization. But that is the ultimate target eventually. Even if we cannot do, some other group might to get inspired from this research and might be able to do it in the future.
Yeah, okay, thank you. Does anyone has further questions?
So, how do you differentiate between intentional and unintentional auditing?
Yeah, so very good question. So intentional movement, they have actually high signal amplitude, signal intensity. So we can use a simple threshold amplitude threshold technique to actually differentiate between intentional and unintentional. So unintentional signal amplitude, they are quite lower compared to the intentional eye blinking. So again, that's why I said that it has to be trained, because your intentional eye blink intensity might be different from mine. So we have to basically train individually the system.
Okay, thank you, Professor Islam. Yeah.
Thank you.
So yeah, the second one, I think is from